Okay, so I'm guessing all of you have been at the keynote today and noticed that there's a lot more to machine learning than just a trainer. And all ML practitioners out there have realized this over time, right? Anyone that had to do machine learning in a production setting realizes it is a lot more difficult than just the trainer. So in the middle here, we have the trainer, lots of magic happening there. But in reality, you need a lot of components before the training and after the training in order to realize your computation. Right? So if you think about it, how you generate data, right, how you split your data between training and dataset is actually part of how you solve a machine learning problem. In addition, because the training data and the machine learning algorithms are tightly intertwined, if you change your learning algorithm, sometimes you have to change your training data. And if you change your training data, sometimes you have to change your training algorithm. So, So we shouldn't be thinking about each of those boxes in isolation, and we should ideally be thinking about an entire system that allows you to solve an ML problem. In addition, many folks that are researchers also care about the middle box there, the trainer. But in reality is, if you have a good idea and you want to apply it into your product in order to improve an actual product, you have to make sure your idea moves from concept to production, and the deployment has to be seamless. So ideally, the people that are doing research in your teams are not using completely different tools from the ones that are deploying those same ideas to production. In addition, as your business grows, the data of your business will hopefully scale with it. That means that if you have a solution that can scale from a small amount of data, a single machine, a laptop, to something that can work on a beefy machine with lots of CPUs, lots of RAM, or even scale across multiple machines, then having a single system that can do that is a lot easier, right? You don't have to, midway through your business, completely change your tools in order to just continue growing and thriving. So, so we built TFX within Google, and TFX is an end-to-end machine learning platform that has all the properties I mentioned before. It allows us to seamlessly scale from smaller datasets to large datasets. It allows our people to move from experimenting to production very easily. And TFX has been instrumental within Google itself. Here's a logo wall. You can see that TFX is used throughout several alphabets. And within Google, several of our most important products, right? So YouTube, ads, Gmail, etc. And as you can imagine, some of those products have pretty large scale, millions of users. So the same product is able to scale at the needs of our company. And earlier, we promised to make TFX available in the open source world so that folks outside of Google can also reap the same benefits that TFX has had for us within Google. So one of the key tenets or key philosophies of TFX is that of portability. We always reuse portability layers when they're available to us. Like, for example, TensorFlow already existed, so we didn't have to rebuild a machine learning computation framework. And Apache Beam already existed, so we didn't need to build the data parallel processing framework. And when those portability layers do not exist, then we actually invested and built those portability layers ourselves. So this is an example of this is ML metadata, and we will be talking about this later in the talk. Now, TFX, the way we built TFX is also pretty modular. So we have available several libraries that help you with your machine learning lifecycle. And those libraries can be used independently, right? So each of those boxes is powered by various libraries, and you can use those libraries without using the remaining of the system. This allows you to plug aspects of TFX into your existing system without having to adopt TFX wholesale. Okay? But beyond libraries, we also offer components, that is, things we will discuss a little bit later, but they have slightly more defined APIs and understand the context of the world around them and allow you to connect those components together. And finally, as of recently, we also offer an end-to-end system that puts those components together so that you don't need to assemble the car, if you will, from its parts. We give you the entire car, the obligatory car analogy. And Here's some of our partners outside of Google that have successfully used several of our libraries, so the low-level aspects of TFX. And to give you a concrete example with Twitter, they had a very fascinating blog. I recommend folks to take a look. And they discuss how they rank tweets on their home timeline using TensorFlow, and how they use TensorFlow model analysis, a part of TFX, in order to make sure the model has the right quality across several segments of the population. OK, so a brief detour here. I mentioned Apache Beam earlier. So what is Apache Beam? We extensively use this in TFX. It's a unified batch and streaming data processing framework. For TFX, we use the batch aspects of it. So Beam has a set of several SDK frontends on multiple languages. And for TFX, we choose the Python Beam SDK. And the portability of Apache Beam was one of the things that drew us to it, because it allows us to realize our computation both within Google and in the open source world. And in particular, there are several runners on the open source world. And one of them is Apache Spark. And that's probably the one that's most pertinent to most of you, since you're here. And this is a Spark AI Summit. OK, so we discussed earlier about libraries that are able to power our components. And libraries are very low level and pretty modular. In order to make the libraries easy usable by folks, you need some more high-level APIs, right? So we have this notion of components in TFX, and we will get into more details about what this means later. But a key thing to understand here is that a single library, like, for example, TensorFlow data validation, can be used across multiple components in a system. Right? So you make good reuse of your libraries because they're modular. So let's actually discuss about what a component is. A component is beyond just a library. It is a packaged binary and a container. It can be run as part of the pipeline, so it can be connected with other parts of the pipeline. So it has very well-defined inputs and outputs. We know exactly what it consumes and exactly what it produces. It has very well-defined configuration. This way, folks can easily configure and change its behavior to match their needs. And most importantly, it has awareness of context. Right? So it needs to be able to get the inputs from somewhere, and that's kind of the state of the world. And it needs to be able to publish its output somewhere, and that's how it modifies the state of the world. OK, so this state of the world allows it to communicate with other components that are upstream of it and other components that are downstream of it. Right? So here we have an example where a trainer produces a model validator sees that this model is available, compares it with the previous model, sees whether it's better or not. If it is better, it says, yes, this is better, please go ahead, proceed. And then the pusher takes it and pushes the model all the way to production, where the model can actually serve and be used to make decisions. So as you can see, this metadata store takes a key part in realizing this ML platform. Okay? So this is new. As I mentioned earlier, whenever a portability layer exists, we use it. And whenever it doesn't exist, we build it. So metadata, ML metadata, is something we built in order to allow TFX to function outside of Google. OK, so most of folks that have been doing ML workflows are probably aware of what's called task-aware pipelines, right? So you have a component, it runs. As soon as this component runs, a following component downstream picks up the results, does its work, and then continues. But the reality, and what we've learned over several years at Google, is that in order to have usable ML pipelines, task dependencies or task-aware pipelines do not suffice. So the realization is that ML pipelines produce artifacts continuously. Components across the system consume those artifacts. And the presence of data and artifacts should actually be able to trigger computation and have a continuously running system that serves production. So these artifacts need to be tracked, and we will discuss about how we do this internally. OK, so first of all, what goes into this metadata store that we've been discussing? We have definitions of types of artifacts that exist in our ML pipeline ontology. So we have models, we have data, We have evaluation results. And those artifacts might have properties, right? Like what is the version of this data module? What is the CL that is, or the PR that this module was created at, etc. Okay. What we also have is records of executions of various components. And those executions keep track of what were the inputs to the component, what were the outputs of the component, and also what configuration was used as part of that run. So we have a record, a ledger, if you will, of all the artifacts that exist in the system, and what was the thing that produced it, and what is the thing that consumed it downstream, et cetera. So putting those things together, we're actually able to create lineage tracking across all executions in the system. Right? So we are able to do a transitive closure up the lineage tree to know what kind of data was used to train this model. Or we can do a lineage walk down the tree in order to see, for example, if we have identified some corrupted data, which models were affected downstream. Okay? So as you can imagine, this kind of lineage queries are very, very powerful. And I will get into some examples now. Because we have this metadata store that tracks the state of the world, we can issue very simple queries, right? We can say, give me all executions of type trainer run, right? So the system tells us, OK, there were 2 runs of the trainer, and here are some properties of it. Nothing fancy. But let's take it a step further. Because we have the lineage tracking we discussed earlier, we not only know that there was a trainer execution, but we know exactly what schema was used in the trainer, which transform function was used in the trainer, what examples went into it. And not only that, but if we walk up the lineage tree, as we discussed earlier, and we can look at the transitive closure of this, we understand everything. We understand not only the data that went into the trainer, but the data that went into the transform function, which might be identical, if that's what you need, or might actually be different. Right? But because we have the ledger of all the artifacts and everything that's happening into the system, we can actually always know what went on. Let's look at some more examples where this is useful. Imagine you've trained the model, and it's not performing very well. One obvious issue might be that the data there's something wrong with the data. It would be great if I can say, for a given model run, give me the statistics of the data that this model trained on. Right? So this is something that's enabled by the ML metadata lineage tracking functionality. And note that this is not saying, here's a bunch of data, give me the statistics of this data. Here's a model. What kind of data did this model train on? Allow me to visualize this. OK, here's another example. The previous example walked up the lineage tree. The current example will walk down the lineage tree. So for a given model, show me all the sliced evaluation metrics associated with it. So you had the trainer, you had the model evaluator that ran on it and evaluated the model, and maybe there were several of those. We can easily visualize them if we want to see how the model is performing. Here's another example. Maybe I ran a TensorFlow trainer a week ago, but because in TFX we have this, the ML metadata store of all the artifacts, I can now launch a TensorFlow job and point it to the data of the model that was run a week ago. So you can go back in time and look at the experiments that were run before. And nothing stops me to do only a single model. I can actually do the same thing for multiple models and compare them side by side. Right? So you can see how you're able to compare the entirety of the state of your ML pipeline, not just a single experiment that the person ran. And here's something that kind of puts the two together. I have 2 models, and they're performing somewhat differently from each other. I wonder why this might be. Let me look at the training data of each of those 2 models, and then overlay the statistics of those data, right? So maybe the models are performing differently because, for example, the fair distribution was quite different between the 2 models. Okay, so as we've shown here, there is a lot of use cases that are enabled by this lineage tracking that the metadata store provides. So this is something related to what we spoke earlier. We can always compare multiple models across runs. But there is also some more interesting advanced functionality we can take care of because of ML metadata. Importantly, we can carry over state from previous models. right? So if a model has trained on X amount of data and then a new batch of data arrives, ideally I don't need to retrain the entire thing from scratch, right? I can just use the state, warm start the model, use the pre-existing weights, apply the updates based on the new data, and then have a new model available for serving, right? So this, as you can imagine, decreases both the runtime of how long things take, so it decreases the end-to-end latency from going from data, new data, to a model, but it also decreases the amount of computation needed. Okay, and you can also reuse previously computed outputs. This was also mentioned in the keynote earlier today, but if you have a workflow where you have data generation, transforms, and training, and you're only playing with the training part of it, then and your data did not change, and your transform function did not change, then there should be no need for you to rerun all upstream dependencies. You only need to run the dependencies that have been poisoned or that have been changed and move forward. So this also decreases the iteration time and also saves resources. Okay, so far we spoke about components. And let's dive into what those look like. Okay, so there's three aspects to it. The two important aspects are the driver and the publisher, and those integrate with the metadata store we just discussed. So what does the driver do? It looks at the state of the world, what is the current state of the world, and depending on what the state of that world is, decides what work needs to be done. And then the publisher is aware of, it looks into all the inputs and outputs that are used by the component, records everything into our ledger, and it's available for later use. Okay? And in the middle, we have what we call the executor. And the executor is the one that actually has lots of business logic regarding what powers this component. What is noteworthy here is that the executor is kind of operating in isolation, right? It doesn't need to connect with the rest of the world, which makes debugging easier, right? It doesn't need to understand ML metadata. It just executes work that it's told to do, right? The benefit of this is that you can plug into the system surgically without needing to understand ML metadata, without needing to understand drivers and publishers, and you can say, I will just customize this function to do my custom business logic that is slightly different from what stock TFX is giving me. So this is a lot of functionality, a lot of flexibility that is probably useful to folks outside of Google. Okay, now the executor itself is often implemented with a standard task-driven pipeline, right? So you could use several components of TFX, their executor is implemented on top of Beam, like the transform, for example, and here's how it would look. This is an example of the executor of the SchemaGen component that we will discuss later. So here you can see that we are actually using the Beam SDK to read data, decode the data into a format that statistics generation expects, produces statistics, and then write the results. Okay. Here's another example of an executor. This time it's a trainer. It's using stock TensorFlow. And you have the full power of TensorFlow here. Anything you can do with TensorFlow, you can do with TFX. And here's another example of a component that is quite simple. It doesn't need distributed computation. It just needs to inspect some simple artifacts and decide whether or not to push a model into production. And its implementation is very simple Python. So as you can see, there's a large variety of how complicated and big or large the executors can be. You can have an executor that does distributed computation over petabytes of data, or you can have an executor that looks at a few kilobytes of data and decide what needs to be done. Okay, so we spoke about components. What's tying all those components together is a unified configuration system. And we will take a look at how this looks like. Okay, so here you can see a pipeline, several components, lots of boilerplate. But the important thing to notice here is that the outputs of one component are inputs to the following component. And those are the artifacts that those components exchange between themselves. Okay, quick back to orchestration. We've talked about components, but we haven't yet spoken about how we orchestrate them. So in TFX, we decided, again, following our portability mantra, we decided to not rebuild what already exists. So there's several orchestrators out there, like, for example, Airflow or Kubeflow. And we built TFX in a way that is pluggable to the orchestration system of your choice, we provide some pre-built orchestration systems, and you should be able to use those patterns in order to customize it to a system for which we don't provide an out-of-the-box orchestrator. Okay, so here's an example of a real TFX pipeline, the Chicago taxi example, that has a simple configuration, and it's realized, the exact same pipeline is realized locally on your laptop with small amount of data on the left with Airflow, and it's also realized on GCP with Kubeflow on the full data set, and you're able to scale seamlessly. Okay, so just a quick recap, putting everything together. We have a unified configuration framework at the top. We have an ML metadata store that allows us to connect components together, and those components interoperate with each other seamlessly to allow you to realize your ML workflows. So we will quickly go through each of those sections and briefly talk about those components, just to give you a flavor of what they can do. So starting with data ingestion to the system, we have an ExampleGen component, and that is powered by Apache Beam. And the purpose of this component is to look at the original source data, possibly even join data, et cetera, and then take this data, put it in a format that downstream components can understand. So we're standardizing the format so that all downstream components are implemented simply and are implemented efficiently when possible. And we also enforce some best practices, right? So this is the entry point into our system. We're able to, for example, by default, randomize your data, split it in a way that prevents leaking of information from training data into eval data, et cetera. And the configuration is pretty simple. Next up, we want to make sure that the data that is going into a system is of good quality. I hope I don't need to convince you that this is important, but I will anyway. But in machine learning, as we discussed earlier, data and code are tightly intertwined. Obviously, if you have garbage in going into your pipeline, you will have garbage out. This is simple. If you want to understand how your model is performing, you have to make sure that what your data looks like first, right? It's impossible to understand the output of a very complicated system, which is the training process, without understanding the input that is going into that very complicated process. It's not a magical black box. It's something that you need to be able to understand. And in general, what we've come to realize over time is that you should treat data as you treat code. So the data needs to be versioned. The statistics of those data need to be versioned. You need to understand everything as much about the data as you do about code. And then obviously, catching errors as early as possible in your system will save you time downstream and will also save you computation and money, right? You don't need to spend expensive training dollars on data that is garbage, basically. Okay, so let's look at one of those components, the StatisticsGen component that looks at generating statistics for your data so that you're able to understand it. Its input is simple. It's your training and eval split that were produced by ExampleGen, and it can also consume serving logs so that you can compare training and serving data in order to detect skews, differences between those data. And this component is also implemented in Beam. So it does its distributed computation, and out come statistics that you can actually visualize, and you can overlay those visualization statistics and compare different data sets to see how different or how same they are. If your training data set and your eval data set is fundamentally different, there might be a problem in how you're splitting your data. And maybe you're introducing biases into your training process. The configuration of this is simple. Here's an example of the UI. We can see distributions of data, quite nice. And you can imagine that using these distributions, you can visualize issues that might creep downstream. So here's an example of the Chicago taxi, again, that we discussed earlier, where we can see that the amount of data we have for the early hours of the day is a lot smaller compared to the other hours of the day. So this might be a good explanation of why our model might not be performing very well on the early hours of the day. And we should be cautious about its predictions when that is happening. Okay, moving on into the schema generation component. This takes the results of the statistics generation, which is the stats on disk, and then the schema takes those, and the SchemaGen takes those and produces an auto-inferred schema.
So in general, a schema should be describing the high-level aspects of the data. What are the types of each of your features? What are the types of each of your columns? What is the domain of each of those features? What expectations do you have on them? What are constraints you can impose on it, et cetera? And there's lots of more functionality. But you can think of it as codifying what it means for the data to be good into the model. And because this can be a tedious process, SchemaGen is there to automatically compute a schema based on the statistics for you. But then after that auto-generated schema is available, you can go in and customize it and say, yep, this looks right, this doesn't look right, this needs to be slightly different, et cetera. So simplifies the process, but also allows you to customize it to your business needs. Okay, so here's the configuration again, pretty simple. And an example of what kind of expectations this encodes. So let's say, again, you're the Chicago taxi application, and you have various kinds of forms of payment, credit card and cash, and suddenly a new form of payment appears. Is this new form of payment is expected or not? If it's not expected, you would hope that some alerts can be fired, and this is the job of the ExampleValidator component. So this component can detect things like missing features, right? So let's say you have a new piece of data that no longer has a company or that no longer has a cash payment, method of payment. Something's up. You might have a feature that has a wrong valency. You were expecting exactly 1 or exactly 2 values, and suddenly you say 3. Your expectations about what your data means is completely off, and any model you produce downstream will probably be problematic. You can also detect training serving skew, as we mentioned earlier, and you can compare the data distributions and look at the drift of those distributions over time, which might say that your business is changing, so you might need to put some effort into make sure you understand this and model for it appropriately. The configuration is also pretty simple, and here's an example of a feature again, company. Maybe a new company appeared in your taxi application, and that is expected. Maybe this is how you do business as usual. You continuously add new customers, or maybe you have a fixed set of customers. So if a new company appears, then that means that there's probably some bug upstream, maybe a typo that completely changes what your model expects. Okay, moving on, transformations. Oftentimes, the transformations you need to perform onto data requires not only map kind of computation, but also global reductions. So for example, generating a vocabulary or generating quantiles or normalizing your features requires one to do 1 or more passes over the data. And that can be tedious, but not with transform. So with transform, you specify a preprocessing FN, you describe the computation you want to realize, and then it automatically figures out the stages of computation that need to happen in order to get the values of those analysis phases, and then it intelligently takes those values, puts them as constant into a saved model, and that is now a hermetic representation of your preprocessing function, right? It no longer depends on your data. It's a pure map function. It's a closure of all your data, but it encodes all the information that existed into your data. In that way, it's not very different from a model. Now that you have this saved model, you can actually use it both at training time, and you can also use it at serving time. And because it's the exact same graph, there is no chance of a training serving skew. The exact same computation is performed when you're training and when you're serving. And that's taken care for you automatically. So what does this component look like? This component is also implemented in Beam. And you provide your user-provided transform code, the preprocessing FN we discussed earlier. And it uses the inputs from the rest of the items in the system. And out comes a transform graph, which is the graph we just discussed. And optionally, you can also materialize the data, pass the data through this transform graph. So you can imagine that if you have a learning algorithm downstream that needs to do multiple passes over the data in order to converge, I don't need to redo my transformations each time I'm rereading my data. I can just pass the transformations through the transform graph we just created, materialize the data in an efficient format, and then my multiple passes over the data will be a lot cheaper. But this is optional. If you don't need it, you don't need to do that. Okay, and here's how the transform component looks. like all other components, inputs and outputs, and also the module file that has the preprocessing FN. And here's an example of the preprocessing FN. You can see here that we're doing a map transformation for the label. No need for any reductions, simple thresholding and whatnot. But you can also see here that we are scaling some features to z-score. And that scale to z-score actually requires a full pass over the data. So what the user writes is very simple, and the system takes care of realizing this computation for them. Okay, so now that my data is available, now that I verified that the data is of good quality, now that I massage my data in a way that is friendly for consumption in the trainer, I'm ready to train. And here's the trainer component. It has the inputs that we discussed earlier, transform graph coming from transform, data coming from the example generation produced earlier, and the code itself. And magic happens, and out comes a model, a saved model. And it's actually two saved models. One model is the one that we will use for inference in our serving system, and another model that we can use for evaluation, for evaluating the quality of the model. Okay, so here is the configuration for this component, pretty simple. And what is in this module file? It's just TensorFlow. So everything you can do with TensorFlow, you can do in TFX. Okay, now that I've trained the model, I have a summary of all my data. I need to know, is this good or not, right? What is the quality of this model? And this takes us to the evaluation component. The evaluation component is also powered by Beam. And it takes input the various splits of the data, or actually the evaluation split of your data, and then passes it through your model and is able to slice, to evaluate the model, and then look at how the model is doing across different slices of data. So I don't care about how the model is doing globally, but how it's doing in different aspects of my population. So if you saw the Netflix talk today, it's the same movie might perform different across different regions, right? And this allows you to actually inspect that and understand it. And out come the results that you can actually visualize. And as you can see here, some of the metrics look quite nice in some slices, but in some slices they're quite bad, right? So if you want to understand your business, you better understand how your model is doing across your entire population and across slices of that population, whether that's for quality, fairness, etc. Okay, and moving on, if we're satisfied with the quality of the model via evaluations, human evaluations, we want to make sure that we're satisfied for programmatic consumption as well. And this is where the model validation component comes in. Very similar to the evaluation component, but here this component can actually take multiple models as input. So you can compare your current production model that is blessed and you know to perform well, take the new model, compare the two simultaneously, and decide whether the new model is better than the old one. If it is, then we stamp the model as good, and it's available for downstream consumption. Okay, and that's where the pusher component comes in. It looks at the results of the validation we just discussed. If your model passed all the quality thresholds you had, it is now usable in production. So the pusher takes this model, pushes it into production, and there's actually multiple serving points it can push to, right? So you can push a model to disk, and then some downstream process can pick it up, or you can push it to TensorFlow serving, or you can push it to Cloud ML engine, right? So you nicely separate your training pipeline. You make sure that your training pipeline produces good quality results. Once everything is ready, push the model into production. Okay, and with this, I would like to ask Ahmed to come in and talk about TFX data parallel processing and the relationship between Apache Beam we just discussed and Apache Spark, which many of you will be interested in.
Thanks a lot. Hello, everyone. I am an Apache Beam PMC member, and we talk about a bunch of TFX components that are powered on top of Beam APIs. And the part that I would like to focus my 5 minutes is how Apache Beam works in close collaboration with Apache Spark, and how all these TFX components that are powered on top of Beam APIs will run on any execution engine, as we call, including Apache Spark. And this was a quick recap. All the components that was marked with Beam logo are the ones that are powered by Beam APIs. And the ones with solid green are open source TFX components. For those of you who are not familiar with Apache Beam, Beam is a comprehensive portability framework for running data processing pipelines. And the vision we have is, as a user, you can write your Beam processing pipelines in any language of your choice. And today we support Java, Python, Go, Scala, SQL. And you can run your pipelines on any execution engine of your choice. Again, we support Apache Flink, Apache Spark, we support Google Cloud Dataflow, and we support a list of execution engines that is, I believe, more than 10 at this point. And the key idea behind the portability is, in one way, Beam is capable of representing pipelines in a portable way that is understood by various execution engines. These are so-called runners in Apache Beam terminology. Once a pipeline is represented in a portable way, our runners can take these and natively translate into what will be most efficiently executed in that specific engine. And this example, for example, this very simple pipeline can be executed on all of these engines, and they will be executed as if it is natively written for that engine. And the other part of the portability is the user end of it. Users are empowered to write their pipelines in whatever language of their choice, and there are APIs that are native to those languages. And whatever user writes in their language of choice is converted to this portable model. And the very key idea here is, in Beam, we don't need to implement for each language, for each runner type of a one-to-one mappings. So we can reduce this n language times m runner to one portable path. And I would like to kind of a little bit talk about where we are today in terms of runners. So just a quick example on Apache Flink. So we have a portable Apache Flink runner. This is used in production. It pretty much has a fairly complete implementation of all of Beam model. And a few missing features are really advanced Beam features that are coming up, and they are not really implemented in most of our other runners. But I know here we are more interested in Spark. And for Spark, we have a very similar implementation for Spark runner that is specific for Java. These are the runners we implemented before Beam offered various languages. So we have a Beam Spark runner that can take Beam Java pipelines and execute on Spark. But again, I think the most interesting part for this audience, given that TFX chose to implement on Beam Python, and we would like to run on Apache Spark, is we actually have a runner that is portable and running on Apache Spark. So we started building this in last couple of months, but we made really great amount of progress in just short few months. And the main reason I think we were able to do this was we learned so many lessons while we were building our Apache Flink runner. So we are at a state that probably in a short while we will start to be able to run TFX pipelines on it. And we are making great progress and putting resources behind this. And I'll make a call to action just before I finish. Like in Apache Beam community, we would love to have Spark community members to join us and help with coding, reviews, testing, or whatever. And I just put it like 2 pointers to Jira issues. If you would like to join us the conversation, these will be a good starting points. With that, I would like to open up for questions. We have like short 2 minutes for questions, but after that, we can take more questions outside the room.
Yeah.
Hi, I had one question.
Yes.
So in one of the slides you mentioned about comparing different models. I was just wondering if the models were entirely different. For example, if you want to do sentiment analysis, if it's LSTM versus CNNs, how do I compare these models? And beyond just training data, what if I want to compare the components and activations of these disparate models? Is that possible?
Yeah, so far I would say the kind of comparison that happens is usually to some degree black boxy. So you look at the prediction of the model and then you can slice it across several dimensions and be able to compare them directly. So be able to compare them on their output. We don't have direct functionality to compare different kinds of models, and to some degree this is a hard problem, right? So you cannot compare completely different disjoint computations. Most of the time, because at the end of the day, you're applying a model to make a decision, you can compare the models on the merit of the decisions they make across the entirety of the population.
Folks, that's all the time we're going to have for Q&A in here. If you want to take it out in the hallway with Gus and Ahmet, that would be fantastic. And let's thank them again for their talk.
Thank you, everyone.